Okay. Right, we'll start with some more observations about the cycle space and the cut space, which we introduced last time. One very fundamental feature of the two is that they're orthogonal to each other. So we had a dot product. Orthogonal means dot product is 0. So C, this claims, consists of precisely those elements of the edge space that are orthogonal to every cut, every element of the cut space. Okay, and the other equality claims the analogous statement the other way around, so that the elements of the edge space that are orthogonal to all the elements of the cycle space, equivalently to all the cycles, are precisely the cuts and the empty set. Right, so it's easy to have one implication, namely the inclusion from left to right. If we have a cut, and that means a set of edges of all the edges across some bipartition of the graph, of the vertex set, and we consider a cycle, well, the cycle has to meet this cut in an even number of edges. If it goes across, somehow, if it wants to end up here, it has to come back. Maybe it fails for at the first attempt, but eventually it has to get back, and so it has to cross an even number of times. Right? So this was an arbitrary cut with a corresponding vertex bipartition, and this was an arbitrary cycle. So every cycle meets every cut in an even number of edges, and therefore not only every cycle, but also every element of the cycle space does that. So we have both inclusions. C is a subset of B orthogonal, and B is a subset of C orthogonal. Now, the other implication is more interesting. So let's look at the first one. We want to show that everything that's orthogonal to every cut is in the cycle space. Given an arbitrary set of edges, assume something weird, that it's orthogonal to every cut. That whenever you come up with any cut, set of all edges across a vertex bipartition, then your given set, meets that in an even subset. And that is what you know. You have a given subset of the edges, and then you know that for every cut, it takes out an even number of edges. Now, why on earth should that be in the cycle space? It's a totally weird, complicated assumption that we're making, and we can't really buy anything for it unless you see something brilliant. Well, I don't, but it's easy to look at the converse, or the contraposition. Suppose our set of edges is not in the cycle space. We want to show it's in the cycle space. Suppose it's not. What can we say? If our set is not in the cycle space, it induces an odd degree at some vertex. So here's our vertex V. The given set of edges cannot be orthogonal to the cut space, because here's a cut. The cut is E of V. That's the set of all edges incident with V, all set of edges in G incident with V. Right, and it meets this set of edges in an odd number of edges, so it's not orthogonal to that particular cut. and therefore it's not orthogonal. It's not in the space orthogonal to the cut space. Okay? So that was easy. How about the other one? If we have an element of the edge space that is orthogonal to every cycle, to every element of the cycle space, but that comes to the same thing, an element of the edge space that meets every cycle evenly. Can we show that this is a cut? Well, what do we want to show? We want to show that it's the set of edges across some bipartition, right? So, given f in the set of edges orthogonal to all the cycles, we want that the graph with edges in this set, f, and vertices as we're given from G, is bipartite. Okay, what if it's not bipartite? Well, then it contains an odd cycle, right? And then F meets this odd cycle, because it contains it, in an odd number of edges. So it can't be in this set. Okay, everything correct? No? Oh, you don't know me yet. No. No. Very bad proof. Okay, so let's take it more slowly. What have we shown? We have shown that this particular graph is bipartite. Right, so we found a vertex bipartition across which F has all its edges. But we want a bipartition such that the set of all the edges across this bipartition is precisely F. Not only that F is a subset of that. So G might have some other edges across this bipartition. So we haven't shown that F is a cut of G. We have shown that F is a cut of this graph. Yeah. So that's not a proof. Okay, so I cleverly confused or fudged necessary and sufficient conditions earlier when I said we want that this is bipartite. Yes, of course we want that this is bipartite, but that won't be enough. Okay, right, so what can we do better? Well, there's a nice trick that is often useful in connectivity theory, and this is sort of related to connectivity here. If deleting edges doesn't work, contract them. So in this argument here, we deleted the edges that are not in F, and we worked with that remaining graph. Then we found it's bipartite, and we said, done, incorrectly. Right? Okay, so let's delete, let's contract rather than delete those edges. Okay, let me fit this on this board here. So contract edges of G minus F. Or rather, contract the component of G minus F, right? All the edges, contract all the edges of G that are not in F. That amounts to contracting the components into contracted vertices. So we have some components. In the graph G minus the edges from F. F is that set of edges that we want to show is a cut. So where are the edges in this picture? Well, let's see. One thing we know is that the graph, the contracted graph, has only edges in F. Right? Because we contracted all the others. We contracted all the edges not in F, so the edges that remain in the contracted graph are in F, so we can't have an odd cycle in this contracted graph. Why not? Well, because we can expand any odd cycle in this contracted graph H. So let me write this down. H is G contract the edges of F. E minus F. We can't have an odd cycle in this graph because if we had such an odd cycle, we could expand its vertices into two paths between the vertices of G that give rise to these edges between different vertices of H, and thereby expand this cycle of H with the blue edges to a cycle in G which contains only yellow edges in these blobs. So this cycle in G now meets F, the blue set of edges, in an odd number of edges. But that's not allowed because by assumption, we started out with F being orthogonal to every cycle, and F is not orthogonal to this cycle in G, with the fiddly bits in here. Okay, right, so now we know that H is bipartite. So H has all these blobs at vertices. With yellow edges in them, connected little blobs in G. But these are now vertices of H. And we can expand this bipartition of H, whose edges of H across are precisely our blue edges, the edges from F, to a bipartition of the vertex edge of G by just replacing each of these blobs with a set of its elements. All right, so we get a bipartition of the vertex set of G induced from this bipartition of the vertex set of H. And now I claim that F is precisely the edges, the set of all the edges across this bipartition. Are we done? We're done if the claim is correct. Is the claim correct? Yes. Have I shown it? No? Yes? Okay. Can you see something missing? Well, I haven't shown you that these are indeed all the edges of F from F, because I haven't shown you that these blobs, which we contracted, do not induce in G any blue edges. Right? We said these are components of G minus F, and we contract them, fine, but maybe there was a blue edge on one of those components as well. Could that be the case? Could there have been such an edge here, in which case this would make a loop in the contracted graph H? Could there be such an edge? In which case, this edge would still exist here, and F would not be shown to, would not have been shown to be a cut. Yeah?
I thought we contracted all the edges.
Yes, we did. But we contracted the yellow edges. So if this blue edge existed earlier, it would just witness the fact that the set of edges across this bipartition of G is not all of F, but there is another edge from F. Could that exist? No, of course it can't exist, because look, we have a cycle here. It's a chord in the, say, a spanning tree in this component of G minus F. Right? That's a connected graph. The yellow graph here on this component, and this blue edge makes a cycle with edges, with yellow edges, and therefore this cycle would meet the blue set in exactly one edge, and that by assumption does not happen for any cycle, because the blue set is orthogonal to every cycle. So yes, we have finished the proof now, and I claim it's correct, but now you can speak and tell me otherwise.
What if we don't have a single blue edge in one of the contracted components, but the connected pair?
Yeah, you can have lots of edges. I mean, you can't have even one edge. If there are more edges, I can make this argument the same way. Just consider one of them.
But if you have a pair, then perhaps the cycle would...
No. I'm allowed to choose the cycle to consider. So consider a blue edge in one of these components. There may be lots of others. Consider one of them. It makes a cycle with yellow edges, with only yellow edges. There exists a cycle in this, on this set of vertices in G that has this edge, this one blue edge, and only yellow edges otherwise. And the reason for that is that this set of vertices is made connected by the yellow edges. Okay, any other questions? But thank you, do ask. No? Okay, so don't rashly believe anything I say. And now, let's move on to something else, and that is fundamental cycles and fundamental cuts with respect to a given spanning tree of G. Any edge of G not in the spanning tree forms a cycle together with edges from that spanning tree, right? Because its end vertices of this other edge have a unique path between them in that tree. And they form a cycle. That cycle contains E, this additional edge, outside the tree and no other edge outside the tree. But only some edges in the tree, and we don't know which. Similarly, and as we shall see in a moment, dually, consider an edge not outside the spanning tree, but an edge in the spanning tree. Call that little f. Then there is a cut, the fundamental cut, df, that corresponds to this little tree edge. And what's that cut? Well, take any edge from a tree. If you delete it, the tree falls into two components, precisely two components. They define vertex set. The vertex sets of these components form a bipartition of the vertex set of G. And G has lots of edges across that bipartition, including this one edge F that you deleted. No other edge from the tree, but lots of edges outside the tree. That's a cut of G, and it's called the fundamental cut, corresponding to this edge F. Okay, and there's a beautiful duality statement here, which should have appeared on your exercise sheet, and due to a fault of mine, didn't, because I thought I'd done it in graph theory 1, but in fact I hadn't. So the duality statement is that given any edges E and F of G, F is in the tree and E is not in the tree, then F is in the fundamental cut, fundamental cycle corresponding to E, if and only if E lies in the fundamental cut belonging to F. Right, so that's how the kind of thing you see in duality all the time, right? E is in dF if and only if F is in CE. Right. So I'm not going to prove that. It's elementary. The interesting thing is the statement, not the fact that it's true. And one can use it, one can do lots of things with it, but it's not hard to prove. Okay, so let's prove something more substantial. That's theorem 195. It has two parts. The second part is a corollary of the first part. The second part is about dimension. We'll get to that in a moment. And the first part is more interesting, and that says that the fundamental cuts form a basis of the cut space, and the fundamental cycles form a basis of the cycle space. Okay, so let's prove that. Fundamental cycles and fundamental cuts are clearly linearly independent. Are they? I've warned you, but sometimes I make true statements as well. So yes, they are. Why are they linearly independent? Well, a cycle, CE, fundamental cycle belonging to the edge E, cannot be generated by any other fundamental cycles, by any linear combination of other fundamental cycles, because this one edge E cannot appear in any linear combination of the other cycles. It doesn't lie in any other fundamental cycles. Okay? So the fundamental cycles are linearly independent. You can't combine any one of them from the others. And the same is true for the cuts. So dF cannot be combined from the other fundamental cuts because its edge F doesn't lie in any of the others. Okay? So they're clearly independent. Now why, or are they, do they generate the entire space? So let's see that for the cycles first. The CE generate the cycle space? Well, let's see. Let's consider our tree, T, that's our spanning tree, and any cycle in G that may contain some chords of this spanning tree. It may follow some of the edges of the spanning tree. We don't know. So take an arbitrary cycle in C that meets T, the spanning tree, in some edges. We don't know which. But without knowing which, we can already see what must be the right linear combination of this cycle for this cycle C from the fundamental cycles. So if our claim is true, if we can generate C from the CEs, how should we do it? What should be the sum? Yeah?
Take all the fundamental cycles of the edges of this cycle not contained in the tree.
Precisely. Precisely. So C has some chords and it has some tree edges. We must take all the CEs with E a chord, with E lying on that cycle, because we can only get that from this one CE. Okay, so we are hoping that C might be the sum over all E in C without, sorry, in G without the edges of the tree. Of all those fundamental cycles, CE. All these E's, thank you, that lie on C but are not in the tree. Right? We do necessarily have to take these CEs. And also, we're not allowed to take any other CEs because we couldn't get rid of their E's. Right? No matter how we continue with this sum, if we take any CE with E not on our cycle C, we have to somehow delete it again because we want to end up with only the edges in C. But we can't by doing whatever we like with the other fundamental cycles in the sum. So C has to be, if the statement is true, C has to be exactly this sum. Well, is it? Okay, here's a brilliant half-line proof. This equality that we want to show is the same as saying that the difference between the two is empty. Right? Minus and plus are the same over F2. So the statement that we want is equivalent to saying that this sum is empty, is the empty set. It's the empty set of edges. Is it? Yeah?
Well, if it wouldn't be, it would be a cycle, but the cycle...
No, it could be a disjoint union of cycles.
Well, it has cycles.
Yeah.
But all cycles contain edges not in the spanning tree. And
Precisely, thank you. Right? So this is an element of the cycle space. Where are its edges? They're all in T. So which subset of the edge set of a tree lies in the cycle space? Only one subset. That's the empty set. Isn't that brilliant? Right, we can do the same for the cuts. consider our tree again, and any cut that we want to generate from fundamental cuts. So this is our given cut, and there are lots of edges across that cut, some of which lie in our tree. And if our statement is true, then there's only one possible sum of fundamental cuts that can make this cut D. And that must be the sum over all F in D intersect T. I write T now for the edge set of T. Of all those. For the same reason, we must take all those df's with little f in our desired cut into our sum, because we can't get it from summing over any other fundamental cuts. These f here, these three f that lie in D and are in the tree, we want them to end up in our sum, because the sum should be D, but the only fundamental cuts they lie in are those that they index themselves, right? So we must have those in the sum, and likewise we can't have any others, because if we had another fundamental cut, say for this edge up here, then we couldn't get rid of it again in the sum by summing over some other fundamental cut, because that lies only in its fundamental cut. Okay, so exactly as before, we need that this is exactly the way to generate D. And is it? Well, same thing. This is the same as that. That's the same as this. And this here is an element of the cut space, which consists of edges not in the tree. Right? So, is there such a set that is non-empty? Is there a cut that consists only of edges not in the tree? Precisely. The graph is connected, the tree is a spanning tree, and if we have any cut of G, all the edges across some bipartition of the vertex set, then the tree, which is a spanning tree, must have at least one edge in that cut. So we can't have a cut whose edges are entirely outside the tree. So the only element of the cut space that lies entirely outside the tree is the empty set, and we're again done. Okay. Right, so we've done that. Next statement is dimensions. Well, that's now an immediate corollary, because we know how many edges the tree has. If n is the set of vertices of G, the order of G, then the tree has n minus 1 edges, right? And the df, the fundamental cuts, form a basis. How many fundamental cuts are there? Well, as many as there are edges, little f in the tree. So n minus 1. Okay, so the cut space has dimension n minus 1, and the cycle space, by the dimension formula that we had last time, must have the complement of that up to the dimension of the edge space in which they are orthogonal, which is exactly what is claimed here, m minus n plus 1, m minus n minus 1, where m is the number of edges of G. Okay, the incidence matrix. a matrix whose rows are indexed with the vertices of our graph. The columns are indexed with the edges of our graph. This is called B. Incidence matrix B. How's it defined? Well, for every edge, E and every vertex V that are incident, we put a 1 there. And otherwise, we have zeros. So V1 perhaps is incident with EM and E1, and it can't be incident with any other edge. Sorry, it could. So let's say here's another one. But every edge has only 2 ones in its column because it has only 2 vertices that it joins. Okay, so that's the incidence matrix. B. Okay, so we can interpret that simply on the strength of it being an n by m matrix as a linear map. Right, so we can multiply that with m vectors, m tuples from our field F2. And these correspond to sets of edges. Okay, so what does this multiplication yield? Well, it gives us an n vector. Let's call it lambda 1 to lambda n. And what is lambda I? Well, lambda I is the dot product, this entry here, is the dot product of the row that corresponds to vertex Vi and this column. What's that dot product? Well, Vi has 1s at all the edges incident with it, but only if they have a 1, these edges have a 1 in F, do I collect a 1 for the summation in the dot product. So this is the number of edges at Vi in F. And the number is, of course, always computed in F2. Right, did you get that? So take any set of edges, any vertex. This vertex marks a row in this incidence matrix and corresponds to an entry in this product. What is this entry? It's the sum that counts all the incident edges at V if they're in F. And the counting is done mod 2. And the result of that count is entered there as lambda I. Okay. So that sounds a bit sort of so what-ish. Think of a little, an example where F is just a singleton set, just one edge. what happens then? Well, one edge is mapped to, for every vi that is not incident with this edge, you get a 0 here. Right? For the two v's that are incident with its edge, you get a 1. Right? So B, considered as a linear map, maps the singleton E, where E, say, is the edge UV, to the set of its n vertices when we interpret this n vector over F2 as a subset of the vertex set, namely the set that consists of precisely two vertices, the vertices of E. So in a picture, this edge E gets mapped to this set. And that's the fact that earned this matrix its name B, because that's the boundary of this edge. Right? The boundary is the set of these two vertices. Okay. I had forgotten that you wanted to say something earlier. Was that okay at the end, or? Yeah. I'm sorry. I wanted to continue with that little proof, but okay, good. Right. So that's the boundary map from the edge space to the vertex space. That maps every singleton edge to the set of its n vertices. Okay. Now, what's the kernel of that map? Remember this. When do we get all lambda I to be 0? Yeah, brilliant. Okay, so which sets of edges, F, get a 0 everywhere? Well, those which at every vi have the number of edges 0 mod 2. Those sets of edges that induce at every vertex an even number of edges. Right, so the kernel of this map B is precisely the cycle space. Okay. Now, let's look at the transpose. So, the pedestrian way to do that is to say, well, the transpose of B, BT, now we have a matrix whose rows are indexed by the edges and whose columns are indexed by the vertices. Right, and we can multiply that with n vectors. Okay. An n vector marks a subset of the vertices. So just as we call the subset of edges marked by an m vector big F for set of edges, we call this big U for set of vertices. And now, what's that? So we now get something that we can interpret as a set of edges, because we get something for every index 1 to m. And what do we get? Well, if we look at the row marked by the edge E, then we multiply that with u to get our entry here, a 1 or a 0. And when is it a 1? Well, this little e here has 1s only in 2 places. Right, namely at its end vertices. These survive the dot product with this, if and only if they lie in that set. So if both these lie in U, you get a 1 twice, so that gives you a 0 here. If neither lies in U, you also get a 0, and if exactly one of them lies in U, you get a 1. So F is the set of all edges that leave U and lie the set of all edges that leave U. Okay. What's the image of this linear map? So which F's do we get? Well, just showed you those. Yeah? It's the cut space. Right? For every set of edges in the image, there exists a U, namely this U, such that it's the set of all the edges between U and the rest. And conversely, for every cut that has is the edges, set of edges of all, the set of all the edges across some bipartition, name one of the bipartition sets U, and then you get precisely this here, you put U there. Okay, so that's the cut space. And now it's perhaps, I'm scared of matrices. So I try to, well, you are not, but I am. And I try to avoid matrices at all costs and try to think of what they do. So what do these things do? What does B do? Well, we know what B does. B is the boundary map, right? We know what B does to single edges, and then we just extend linearly to get what B does on any set of edges. We just sum up what it does on the single edges. How about B transpose? Well, as you remember from your linear algebra, when we have B going from the set of edges, or the edge space to the vertex space, then we can look at the linear forms on V and the linear forms on E. So these are the homomorphisms from the vertex space to F2. And each of those gets mapped to a linear form on the edge space, a homomorphism from the edge space to F2. Right? How? Well, given a homomorphism here, and incidentally, that's the same as given a subset of the vertices. Why? Because a homomorphism from the vertex space to anything is defined by what it does on the single vertices because they form its standard basis. So we have to say what phi does on the single vertices, but that's exactly what a subset of the vertex head tells us, namely it assigns a 1 to those vertices in it and a 0 to those not in it. Okay, so given a subset of the vertices, or equivalently given a homomorphism, a linear form from the vertex space to F2, we want a linear form on the psi, on the edges. How do we get it? Well, it doesn't matter. We take any element of the edge space, take the boundary, that's a set of vertices here, perform phi on it, and we get an element of F2. And that's what we assign this to. That's our map psi. So that's completely standard. You heard it in linear algebra, and you'll get it again in topology, or have already had it in topology. But it explains why these are, it explains a little better what they do, rather than just in a pedestrian way looking at what they count, what these dot products count. So the other matrix I want to show you is the adjacency matrix. Okay, so the adjacency matrix is a square matrix, n by n matrix, A. So both the rows and the columns are indexed by vertices. And it has a 1 wherever a vertex and another vertex are adjacent. Right? So if Vi and Vj form an edge, then we get a 1 in position ij, or position Vi, Vj. And if they're not adjacent, we get a 0. That's the adjacency matrix. So let's look at what it does. It works on n tuples, which we can interpret as subsets of the vertices. And what does it do? If we take a subset of the vertices, let's call it the set U, and we multiply that with a row corresponding to Vi. Well, what does it count? Vi has a 1 at all its neighbors. And that 1 survives the dot product if and only if that neighbor happens to be in U. So this entry here is the number of neighbors of Vi in U, and this, of course, as always, is calculated mod 2. So this, interpreted as a set, is the set of W's with an odd number of neighbors in U. Okay? Questions? Good. Why is that interesting? Well, it isn't interesting. But it becomes interesting if I throw in yet another matrix. That's the diagonal matrix. N by n, that has in the diagonal the degrees of the vertices. So D as the degree of D1 all the way to the degree of Vn. And zeros elsewhere. Call that D. And now we have a really interesting characterization, not of A, but of A plus D. So A itself has zeros along the diagonal, right, because it has ones only where we have adjacencies and no vertex is adjacent to itself. But if we add D, then what do we get? Well, you won't see that now, but I'll show you. We'll get B transpose. Right, and there are, you can just verify that, check that from the definitions. It's tedious, as always, with matrices, sorry, but it's easy. You just have to sort of go through the positions and do the dot products and see what happens. Why is it interesting? Well, because this here is the boundary operator followed by the coboundary operator. I didn't tell you that this is what BT was called, but I showed you the diagram that justifies why it's called that. Okay? And that indeed is an interesting animal, BBT. And in a graph, that's just that. This is called the Laplacian of the graph. And that is a discrete version of an operator that comes from elsewhere. You have it in differential geometry. You have it in clustering. So there is something called spectral graph theory, where spectral is code for, has to do with eigenvalues. Now, what eigenvalues? Eigenvalues of the Laplacian. So there's a whole branch of graph theory called spectral graph theory. That is the study of the eigenvalues of the Laplacians of graphs, and of course what they tell you about the graph. And they do tell you a few things. And there is spectral clustering, which clusters points in a data set by calculating eigenvalues of this Laplacian of a suitable graph with edge weights. So edge weights tell you how far apart these points are, and then you get a graph, a complete graph with edge weights, and you compute its Laplacian, and you can do some clustering from there. Right, so it is important, and this version of it, boundary map, circle, coboundary map, is, to my taste, the more natural one than having some matrices we don't understand multiplied with each other to give something we don't understand either. So, but maybe that's a matter of taste. So, there we go. Any questions? No. Then, we now do something really different. And I've already used two boards again. This thought was meant to be for what's coming now. But, there we go. We're going to talk about graphs of all things. Let's ask ourselves the question, what kind of cycles do we need to generate the cycle space? By definition, we can generate it from all the cycles. It is what all the cycles generate. Can we generate it from a subset of the cycle space? Well, there's an exercise that you may have seen already on the first sheet that you should prove that the induced cycles are enough, and another part of the same exercise that asks you to prove that the geodesic cycles are enough. Right? Geodesic cycles are cycles where the distance between two vertices on the cycle is the same as the distance of those two vertices in the graph. So the graph doesn't have shortcuts. Those are geodesic cycles, and they also generate the cycle space. The fundamental cycles generate the cycle space, as we just saw. And I'm going to show you another example. And to motivate that, let's look at a plane graph. Right, so this is a plane graph, and all its cycles, for example, the yellow cycle, which will appear in a moment. Oh, you can't distinguish yellow from white. Yeah, good to know. I'm keeping the really strong colors in reserve, but for when I have something important to say, which hasn't happened. So, okay, can you see that? That's meant to be orange, it's yellow. Well, okay, so let's look at any cycle in this plane graph and see what we can generate it from. And the answer is from the face boundaries of the faces inside it. Right, easy. We just sum up over all these cycles as sets of edges, and every white edge in there will be summed twice, once from here, once from there. But the yellow edges will be summed only once. Okay, and they do appear because they also lie on the boundary of these faces. So in a plane graph, the face boundaries generate the cycle space. They generate every cycle, therefore they generate the entire cycle space. Right. So Tutte, Bill Tutte, one of the sort of giants in graph theory after the Second World War, starting his work in the 1940s. He died some 20 years ago, I think. He achieved a real feat. He divorced this observation from planarity. So he proved something like, in any graph, the cycle space is generated by the which, if the graph happens to lie in the plane, will be the face boundaries. So can you write down a list of properties of the face boundaries which are enough to give you this proof, so that we don't need to appeal to the topology of how they sit in the plane? Not so easy, is it? So I'll tell you the list of properties, and it's very easy. We call them peripheral cycles. And that's now in any graph, not just in a plane graph. If it doesn't have any chords, if it's induced, and if it doesn't separate the graph. If its vertex set doesn't separate the graph. So that's true for faces, for face boundaries, right? Well, not always, but in a three-connected graph. In three-connected G. Well, you can't have a chord across a face boundary through that face. Could you have a chord outside? Well, you could in principle, but if your graph is three-connected, then you can't, because the end vertices of this chord will separate the graph, right? So let me try and find another color. Can you see blue? Can you see blue? Yeah. So if we had this chord somehow going around the outside, I claim that it separates these two segments of the cycle from each other. And the reason is you can complete it to a circle through the face, and then you use the Jordan curve theorem. Right? So the face boundaries are induced, and they're also non-separating. Why? Well, you can't have vertices outside and inside, obviously, in a face boundary. And if you had two components of G minus such a cycle, such a face boundary, and both components were outside, well, they would attach to the face here and there, and you could find a two-separator again between these two components. Right? They can't attach because of planarity in some overlapping kind of way. So face boundaries in a plane graph have this property that they're peripheral, induced and non-separating. And Tutte now proved that in any three-connected graph, the peripheral cycles generate the entire cycle space. Okay, so much time? Yeah, we've got 10 minutes. That's easy. Let me show you the proof. Oops. So we'll do induction on n. N is the set of the number of vertices minus little b. Little b is the largest order of a component of the rest. If there is no component of the rest, so if this is a Hamilton cycle, then we put little b equal to 0, and then n minus b is really, really big. So that's not the induction start, that's the induction end, if you like. Okay, so once more. We consider a cycle, and any largest component, and the order of that component is little b. And n minus b is our induction parameter. We call it k. Okay. How does the induction start? I can't do that to first years, but I can do it with you. It starts with k equals 0. What does that mean? It means that n minus b is 0. So b equals n, the order of the biggest component, or any biggest component, equals the order of the graph minus c, equals the order of the graph itself. But that can't happen, because we have c given. We want to generate our c. Okay? So when we get to apply this, it won't happen. But it's a true statement. So for all cycles C with the property that the largest component in the rest equals the order of G, the size of it, the moon is made of blue cheese. Okay? So it's always true, and that's what we use as the induction start. So we're going to build a real edifice on that. All right? Okay. So, first case. What if sorry. What if C is a Hamilton cycle, if it has all the vertices of G? Well, G is 3 connected, it can't be just this cycle, so there is something else to it. But there is no other vertex, so the something else has to consist of chords. The C has at least one chord. Pick a chord, and then you get 2 cycles induced by this chord with 1/2 of C. And C is clearly the sum of these 2 cycles C1 and C2, because this chord here cancels, that lies in both Ci, that cancels in their sum, and the sum is precisely C. And all we need to check now is that C1 and C2 have a smaller induction parameter. Do they? Yes, they do. The induction parameter is smaller because the number of the size of any biggest component of G minus Ci is bigger, so we take away more from n than in the case of C, where we couldn't take anything away from n. Why is it bigger? Well, the G minus C2 consists of all these vertices, and there are at least 1, because that's a proper chord, so we're not introducing a double edge, and likewise for C1. Okay, C1 and C2 appeared earlier in the induction, and C is the sum of those 2, and now whatever generates C1 and C2 will also generate C. Okay, so that was a case, not the base case for the induction, rather the opposite. It was a case, and now we're in the other case where C does not contain all the vertices. Well, then it does have components. For example, it has this component B, which is a biggest component. Let's pick a biggest component. And that sends at least 3 edges to C, because the graph is 3 connected. Let's look at 2 of them. And they divide C into 2 segments and ask, is there a C path in G from one to the other segment? Is there a path in G that has no vertices other than its ends on C, and avoids these 2 neighbors of B? It might or might not be the case. And if it is the case, then I claim we're done again. And I'll show you some cycles. Now, so from these two vertices where this path hits C, we can go around C either of two ways. And each of these two ways combines with the path to a cycle. Right, so the other way also combines with the path to a cycle. So we get two cycles whose symmetric difference is the original C. That's fine, as long as these two cycles come earlier in the induction. And they do, because look at the blue cycle. There is a component of the rest, G minus the blue cycle, that contains all of B, and in addition, contains this vertex here. And likewise, for the yellow cycle, there exists a component of G minus the yellow cycle that contains all of B plus that vertex. So the biggest component in the rest of G is going to be bigger for these two cycles, yellow and blue, than it was for C. So the induction hypothesis holds for those two. They can be generated from the peripheral cycles, and therefore so can C. Okay. Now suppose there is no such path. Otherwise we're done. If there is no such path, then I claim that B has in its neighborhood the entire cycle C. Why is that the case? Well, suppose this edge wasn't there. So suppose this vertex of C was not a neighbor of B. Then we could find a path from that. I'm running out of colors now. Okay. We can find a path from this vertex to C minus the nearest two neighbors of B along the cycle. So from this vertex that is not a neighbor of B, we can go either way on C until we hit a neighbor of B. These will be distinct because B has at least three neighbors on C, right? And we can find a path from this to the rest of C, because these two vertices don't separate that. Or say we find a path from here to B, right? With three connected. So from this vertex, we can't separate this vertex from B by those two vertices. So pick any path that avoids these two vertices, any path in G that starts here and ends up in B. And before it gets to B, it must go through C. Right? Okay. But then, this is exactly the situation which we said didn't exist. Right? So we have found two neighbors of B, these two, and a path from one of the two segments to the other of the two segments outside G. We just follow this path to B and stop the first time we hit this other segment. Right, so we know that B is adjacent to the entire set C. And also, C doesn't have a chord, right? If C had a chord, that would also be this kind of path. Join any two vertices of C by an edge that is not in C. There's a vertex there, there's a vertex there, and the end vertices of that chord don't separate this segment of C from that segment of C in G, so you can find the path around. Okay, so let's remember what we have shown. All the vertices of C are neighbors of B, the component B, and C doesn't have a chord. Now, what we still need to show is that C doesn't separate G. So we have B in here, adjacent to everything on C, and suppose there was another component B prime that C separates from B. Well, then this B prime again sends at least 3 edges to C because the graph is 3 connected. And inside B prime, we can join the ends of those 3 edges here up by a single path, or we can at least find such a path with 3 of its vertices sending edges to B. Okay, and now we do the last little argument, and we again find suitable cycles. So one of these cycles is this one that are smaller in the induction than C. This one here, why is that smaller? Well, because it leaves a component that consists of B and something else. Similarly, this cycle here is smaller. And then there's a cycle that goes round. And that is also smaller because it leaves a component that contains all of B and this vertex. So all these 3 cycles come earlier in the induction process than C does, and their symmetric difference is C, which completes the proof. Questions? Yeah.
Can you reiterate why the green path in the middle picture is forced to cross C before it...
Yes. Yeah. So it's a path from this vertex here to B. Okay? C, the entire C separates any vertex outside from B. The first vertex on this path, other than the starting vertex, where can that be? It's not on C, it can't be in B because it can't go into B, so it must be outside. This outside vertex is separated from B by C because it lies in some other component. Okay. Any other questions? Right, then I have a question. The proof is correct, don't worry, I think. But how about the induction? We never somehow got to the induction start. We didn't connect to the induction start. So there's something fishy going on. We always reduced to an earlier case, or did we? Right, imagine all the possible cases of C's. We said, okay, given an arbitrary C, we can find some other cycles that are earlier in the induction, maybe one or two or three. Okay, and for those we assumed we could already prove the statement. Well, how, if we did it in a pedestrian way, if I was to prove it for this one, well, then I could reduce the statement for this cycle to the statement for another 2 or 3 cycles that come even earlier in the induction process. And we kept doing that ad infinitum.